Hi everyone. So today we're gonna talk about divisibility in GCD, greatest common divisor number theory. This is probably introduction to number theory in particular, divisibility and concurrence in general. So let's just walk through the problem. So there are some theorems that you should actually know, or more like axioms than actual theorems. So first of all, let's go. Uh, let's go over the divisibility. For integers a and b, b divides n is denoted by a is a proper divisor of b. This denotes proper divisor b if and only if b is in the form. Okay, this is just wrong. So it's gonna be a is in the form of b. B is in the form of aq for some integer q. This is equivalent to saying that b is a proper divisor. A is a proper divisor of b, or b is a multiple of a and q. So what it actually says is that if we have some variable, let's say we have some number 2, then some number and b is equal to 6. By our assumption, b2 is a proper divisor of 6 because it can be written as in the form of 2 times 3, where q is denoted by 3. This is what is called divisibility concurrence. Well, it's actually pretty intuitive by this lemma. This is just a proper definition in this in some sort, I guess. So it implies that a is a proper divisor of 0 because no matter what number you divide 0 with, you're gonna get 0 still anyway. And 1 is a proper divisor of a, yeah, and divides a particular, yeah. So these axioms are actually really useful in our daily lives. No, I'm not gonna say daily lives though. They're actually really useful when you try to apply some stuff and come up with a lemma. Okay, now let's go through some theorems. Okay, so one of the theorems is transitive if it's given that d is a proper divisor of m and m is a proper divisor of n, implies that d is divided by q, and this is really easy done by concurrence. We just know that d is then m is in the form of some let's say qn, and if you know that this is a proper divisor of qd, and then if qd divides nm, then qd, then n, then d should divide m too, if it's divisible. Yeah, just a commutation of some sort, I would say. Okay, now linear combinations. So if d is a proper divisor of n1, and d is a proper divisor of n2, it directly implies that d is a proper divisor of n1, a1 plus a2. This also applies for commutative variables such as minus or multiplication or division, but division should not be 0. This is just easily done since we can actually denote the n1. We can actually commutate it like this, the form of like this, and if we know that those individuals are actually divisible by 2, then this is divisible by 2 too. So this divides this, so by our lemma. Now let's say cancellation. Cancellation is relatively easy. I think intuitively you can already denote this number. So antisymmetry, yeah. So if it says it implies, since both of them should be equivalent, the antisymmetry of the order is traversal times here because the number can be negative of some sort. Yeah, it's pretty intuitive. So now let's walk through some problems. Let's say prove that the product of two consecutive positive integers is divisible by 2. Now, looking at this comes really handy. If we can prove that some number is sorry, two numbers are in the sort of 2n and 2n plus 1, they're both consecutive. Either this one is first order, or second one is the first order, or reverse. Then this is pretty niche, since the product of this is 2n, and we know that 2 is a proper divisor of 2n. So this should be done really easily. Now for p2, we can prove that n3 is divisible by 4. This is equivalent to this 4, n minus 1. And knowing the concurrence, this actually takes the boundary of 3 numbers. let's say 1, 0.1, 0.2, 0.3, then boom, here we take some value. Let's say p is a proper divisor of n, then 3, then we already know that it divides, and minus 1, it one of those should be even, in the form of even. If none, then it actually simplifies to other ideas, yeah. Sorry, I'm a little bit sick today, so hopefully this can be done really easy. So this is just n minus 1. This comes from the idea that if in the form of, for example, 10 denotes like this. 10n integer is just 10n times 0, 0, 0, n. If we can prove that this minus 1 is always equal to divisibility by 9 and 11. Or what notation actually helps us is that we can actually, if n, look, so this just becomes 99999 n minus 1 times n minus 1. You know this is the proper divisor of 9, so the notation that we can generalize the formula for n9, divisibility for 9. Yeah, this just comes from the lemma. Okay. Now, primes and algebraic structures. A prime number is a number which is in the form of p1, meaning that it's greater or equal to 1, and whose only positive divisors are 1 or p. Let's say for the base numbers 1 until 10, it's 2, 3, 5, 7. Since the only divisor of 1 is 2, 1, 2, etc. Now here, this is the definition of composite numbers. It can be written as the sum of both numbers. Yeah. So here we can actually use Sieve Eratosthenes to denote our the first 100 prime numbers. So this technique, what it does is we find some congruent value. Let's say we have some value 3. This is just wrong, right? Never mind. So by our lemma, we can actually denote the number of prime numbers. This is prime. Why I don't know why it's not circled, by the way. Okay, never mind. So if I can find this prime, then all of these divisors are actually not even numbers. Not actually prime numbers. They're composite. So we can cross those out, and we find that they're some of the computation. Now, some of the problems here are really interesting. I'm gonna leave the link here below. Now, let's walk through. I think. Let's go. Jane writes the integers from 1 till 2000 on a piece of paper. She erases all the multiples of 3, and then the multiples of 5, and so on, erasing all the multiples of each odd prime. How many numbers are left when she finishes? Well, this is really an easy problem, since we can actually denote all the prime numbers in the form all prime. This directly comes from the lemma, since Eratosthenes. The only numbers that are going to be left are powers of 2. So 2, 4, 6, 8, 16, 1 is going to be also left here, since we 1, 16, 32 till 1024, which is just 10. So there are arbitrarily large 10 numbers in the source and 11 numbers. So the answer for this is just 11. Now for number 2, find all primes p such that p 1994 plus 1995 is a perfect square. This comes from the idea that all those primes are actually in the form of p. We can actually factor those, yeah. So in the form of p, yeah, such that n, let's say n plus 1, let's say n squared is equal to this number. If we can factor this out and find some congruent value, and we can find the value of p, which can be denoted by y. Now find the largest divisor of n, and that's less than 10,000. This looks like a really nasty problem, but actually it's really easy. We can actually factor this out really beautifully. This, I think, is going to be left for you as an exercise. This is just basic, because by geometric sums we can convergence, we can prove this lemma actually works, since x minus y and x was. Yeah. Okay, now let's go through the division algorithm and walk through some problems right there. So division algorithm. So for any integers a and b such that b is greater than 0, there is a unique integers a, b, q, r. This is easily done if we know the division algorithm for any natural positive integers. Let's say 4. For b and q, we can actually note this as b 1 plus 1. C, 4 can be noted as hence proven for our will. Here is the congruent example here. If we divide, this also comes from the lot of a Chinese remainder theorem, which we're going to be talking to through the next video, and more of the some samples. Now, some of the problems are necessarily hard without the prerequisite studying here. Okay, so we can actually extend the division algorithm. We can actually extend the division algorithms through this. If we can actually, so we can actually extend the division algorithm for all the polynomials in the form of, let's say, p, x in the form of, we can say real rate, real polynomials, or Ri. We can extend this in the form of Ri, which is more congruently done, and yeah, this just comes from the lemma here. We can actually prove that it can be such that p, let's say px, we can factor it to actually some rx let's say fx plus some r, let's say sx. So the degree of s is actually should be less than p. This, and the degree of rx plus y should be equivalent to p. The degree is just nth term of a polynomial such that like x n to the power of n if we denote it. Now Bizet lemma, it's just an extension, I think. GCD AB, we can find some number y and x and y so that we can actually prove them. Here we can actually find the GCD of 12, 8, and 18 to equal to 6. 6 is just 30. Here's a mistake. Wait. So it's so it's 18 to minus 30 plus minus 1. Yeah, this should be like this. Sorry. Some of the fucking are crazy. Here are some problems. Now, yeah, here, GCD and LCM. So the greatest common divisor is, you're probably familiar with it once you were a child, when you learned some of your prime trees. We're gonna prove some examples of least common multiple and GCD in particular. Why does this come from? Where does this come from particularly? So I'm gonna walk through the blank page. So here, let's say we have some two numbers a and b, right? A, b, and they're all natural greater than 1. Let's say a and b are in the set of natural numbers, where a and b are all greater than 1 or equal to 1, it doesn't matter. So let's say just equals for this instance. So then we actually have some prime numbers p, I, p1, p1, p2, p2, and etc. Now let's say lambda 1, and this is a part of lambda 1 and lambda 2, where they're denoted as powers greater than 1, greater or equal to 1. Now what GCD actually does is we take the lowest term and like least, let's say mean of ai bi some number. The same for LCM, but instead of taking the minimum number, we take the maximum number of both numbers. Since if you take the maximum number, we know that this is just the we know that the polynomial of this form fits into this. Then it doesn't actually matter what order, if it's a greater than b or b is greater than I. We're eventually gonna come constants of, so b times b plus a plus b by lemma. We're gonna find that AB is actually equal to LCM plus GCD. So this is how it's denoted, yeah. Now, to actually find this, it's not that hard to prove, but this is a really useful lemma, especially when you're actually trying to compute stuff. We can actually do it in O root of n. Root of n. By the way, I wanted to actually introduce you to some topic that is not in this handout. It's Euclidean algorithm. Euclidean algorithm, what it does is, we have some numbers a and b greater than 1. If we want to find the GCD, we can actually use the recursive formula. A, b is actually really equivalent to GCD a minus b, or b minus a. This is a really useful lemma, since we know that both of the numbers are actually by our theorem 3. Let's go over here. We know that the linear combinations actually apply. So instead of doing this, we can actually put the mod here, modular. We're gonna cover modular arithmetic in the next video, but here I wanted to denote an interesting lemma, how this actually works. Although some of those should be really intuitive. Now, let's walk through some problems to get started. Let's say this one. Now let's do I'm not gonna do all of the problems, but I should cover the basic ones. Let's do this one. The IMO problem. A much simplified one, but never mind. Yep, much simplified one. XY squared, okay, never mind. And then let's choose a new problem here. Let's choose this one, right? Sure. Okay. Now for this, it's 4 4 4 4 f of n. Okay, so the sum of digits. So this is just n is just 4 4 4 4 f of triple n, right? So so if we divide here, we can find that this is actually equal to 4 times 1 1 1 1, or 4 times 11 times 101. Here it's actually really, the idea is really beautiful. It's really beautiful, since what you essentially do here is that you find some value here. Let's say denote the sum of the digits n here. Wait. So this comes from the lemma that 404 times 11. Okay, sorry. This can be factorized in the form of 444. 4444, which is also really intuitive. Now we can actually compute this for 4444, but we wouldn't actually do that. So we can actually find 11 though. 11 here is just really an order of symmetry. Let's say 11 squared is 121. 11 cubed is 1 2 3 2 1. 11 tripled is 1 2 3 4 5 4 3 2 1. You see the order of symmetry. Now, how do I actually compute this? Well, we know the degree of n. We can prove that the sum of numbers here, n plus 1. This is in the form of just n plus 1 times 2 times 2 divided by 2 times 2 minus n. This is just n squared. The sum is just n squared. Yeah, this. Now, for 444, 4444444 squared. The idea also comes up to 101, since 101 to the power of 1 is just 101. 4 to the power of 2 is just 10201. 4 3 is just 102030201. Let's keep the digits here. And we can actually find the proper surrogate here. So it denotes a beautiful idea here. The rest is left as an exercise for the reader. These problems are come from the Justin Stevens Intermediate Number Theory textbook. So if you, it's open source, so you can actually check this. Okay, now for this problem, ABC such that, okay, так, okay, so then A minus 1 should divide A, B, C minus 1, B minus 1 should divide this, and we can actually factor this out and find all the possible scenarios here, which is just pretty intuitive. Now for let's go through some Putnam problems though. Okay, let's say subsequence be eminent integers. Okay, this has an interesting idea. I don't want to spoil it to you since it's going to be really interesting once you solve it. So come a look at this and bye. If you need any suggestions or walk through some problems, I'm probably going to do it in the last video in this playlist, since I want you actually to walk through the problems, since you're gonna understand the coursework if and only if you actually do the problems here. So yeah, the handout will be probably available not now. I'm gonna leave it in the comment section later. So thank you. I hope you found this video well. And if you need any suggestions for me, or if you're struggling with this, and you can leave your suggestions or comments down below. Yeah, so bye. Hope you enjoyed this video.